Things got out of hand very, very quickly. I'm talking about the whole coronavirus thing. A couple days ago, we got a notification saying that we were going to be released for spring break, and then the week after spring break, classes would be held online. Now, we have just been given information saying that classes are going to be held online until practically the middle of April. April 14th, to be exact. I don't know how I'm going to deal with these videos. I mean, I'll be at home. I won't really have a recording setup. Although, to be completely honest, I don't really have a recording setup here. It's just my microphone, my laptop, and my hard drive. But this is going to be very, very interesting to work around. I'm going to have the week for spring break to think about this, so it's not really something that I'm going to consider now. I'm going to study as if classes were happening like normal. Hopefully I will come up with a solution before I have to resume online classes the week after spring break. But enough of that. Let's do some statics. Let's learn about second moments of inertia. If you have a bunch of forces that are acting on an object, and those forces are proportional to an infinitesimally small area that they are acting upon, then we can say that the equivalent force, the delta F, is going to be gamma times y times dA. Then we can say that that delta capital F, the force acting upon that specific infinitesimally small area, is going to be equal to gamma times y times dA, gamma being a specific weight. We can use the same logic that we were using for the first moments to find the resultant force acting on the object due to all of these combined delta Fs, where the resultant force is going to equal the sum of all the delta Fs, which is going to equal gamma times the sum of all y dAs, which is going to equal gamma times the integral of y dA. If we calculate the moment produced with respect to x, we get that the moment with respect to x is going to equal gamma times the integral of y squared dA. This part right here, the integral of y squared dA, is the second moment of inertia. That being said, the second moments of inertia with respect to x and y are as follows. The second moment of inertia with respect to x is the integral of y squared dA, and the second moment of inertia with respect to y is the integral of x squared dA. Much like the first moments, we have two variables here that are not the same. Finding the second moment of inertia with respect to the y-axis, you need x, and finding the second moment of inertia with respect to x, you need y. Now let us consider this funky-looking object. We have our infinitesimal area dA, and this area dA is going to be some distance r away from the origin. dA is also some distance x along the x-axis, and some distance y along the y-axis. Let's also say that this funky object has some area A. We can find the second moment of inertia, but we are going to, instead of finding it with respect to a particular axis, we are going to find the polar moment of inertia. J0 is equal to the integral of r squared dA. But as we are about to see, this polar moment is actually related to the rectangular moments. We know because of Pythagorean theorem that r squared is going to be equal to x squared plus y squared, meaning that J0 is going to be the integral of x squared plus y squared dA, or the integral of x squared dA plus the integral of y squared dA. See where I'm going with this? Which is finally just going to be equal to the sum of the second moments with respect to each axis, meaning that we can find the polar moment by using this formula and integrating, or we can find the polar moment by finding both of the rectangular second moments and then adding them together. Let us consider another goofy-looking object. We can simplify this object down a little. In fact, we know that if we make this object into a thin strip with the same area, and we place it some distance away from the x-axis, that it is going to have the same second moment of inertia with respect to the x-axis. We call this radius the radius of gyration. It's like this. We have this strip with an area A, which is the same area as our goofy object, and it is going to be some distance away from the x-axis. This distance is going to equal k sub x, or the radius of gyration with respect to x, where kx is equal to the square root of the second moment with respect to x divided by the area. Similarly, we can find a radius of gyration with respect to the y-axis, some k sub y, which is going to equal the square root of the second moment with respect to y divided by a. Lastly, we can find some polar radius of gyration. I'm going to do it over here. Here we have some ring with radius a, where k sub naught is going to equal our polar radius of gyration. Following the patterns that we had set before, our k sub naught is going to be equal to the square root of j naught divided by a, j naught being the polar moment of inertia. J naught squared is also equal to kx squared plus ky squared. With all that out of the way, let's talk about parallel axis theorem. Let's say that we have this funky looking object. This object has an area A and a centroid located at point C. We know that the second moment of inertia with respect to x is going to equal the integral of y squared times dA. But here's the thing, integrating this directly is kind of tricky. I mean, this is just a randomly drawn shape, but even if it wasn't, you'd still need multiple integrals to be able to solve it, which is not fun. But there's a little trick that we can play, the parallel axis theorem. Let's say that there is an axis running parallel to the x-axis that is running through the centroid. We'll call it b prime. There is some distance between b prime and the x-axis, and using all that information we can write, finally, the parallel axis theorem. I is equal to I bar plus a d squared, where I bar is the second moment of inertia with respect to the axis running through the centroid. It is with respect to b prime. This means that if we have literally any axis that is parallel to a certain axis, that we can find the second moment with respect to that axis. It is extraordinarily useful. If you were given the moment of inertia with respect to, say, an axis running through the centroid on a table, and you calculated that, then what you could do is simply calculate the second moment of inertia with respect to the axis using the parallel axis theorem. Now let's take all of this and kick it up a notch with the product of inertia. The best way that I can describe the product of inertia is it is the second moment of inertia with respect to both axes. Strange, yes, but we'll figure it out. Instead of being just the integral of x squared dA or y squared dA, it is the integral of x times y times dA. We can also make a parallel axis theorem for the product of inertia. Ixy is equal to I bar xy, which is the new product of inertia with respect to our new axes, plus x bar times y bar times a, where x bar is the distance that our new x-axis is from the old x-axis, and y bar is the distance that our new y-axis is from the old y-axis, and a is just the area of the object. It's 9 o'clock, and I will be damned if I try and figure out principal axes tonight. To me, trying to decipher principal axes are like handing a monolingual the Rosetta Stone and asking them to translate it. I just don't understand it at all right now. So I'm tabling that. This was good though. On to calc. Lagrange multipliers are a little hairy, but they aren't impossible. So for my own sake, I'm going to go a little slow. Last time we learned about analyzing points on the boundary of a domain by parameterizing the domain curves. But by using Lagrange multipliers, we don't need to do that. What we can do is we can find candidates for the maximum and the minimums by studying level curves. Let's say that we're given the following function f of x, and that the boundary can be oh dear. And we can say that the boundary, the edge of the domain, can be given by the function g of x, which is equal to some constant. Let's draw a rough sketch of both of these shapes and see what happens. This is g of x. It is a circle of radius 1. Now we know that there is not a singular shape here, rather there are multiple level curves. For every constant that you set f of x equal to, you are going to get a different level curve. There are two in particular that we're looking for. This thing right here is an ellipse. Now take a look at these two level curves of f of x. Here is one of the level curves that we are interested in. As we can see here, the ellipse intersects our boundary circle. Here is another level curve. As you can see, our ellipse intersects the circle in two different places. Now, my friends, what we can say is that these 2 points are going to be candidates for maximums, and these 2 points are going to be candidates for minimums. We can put this in mathematical terms. Grad f is going to be equal to lambda grad g. We can calculate both grad f and grad g, and say that lambda grad g is going to be equal to the grad g vector times lambda. We multiply each of the components by lambda. What this gives us is a system of equations. Because much in the way that if your grad f function equals a zero vector, we get this system of equations. Because if grad f equals lambda times grad g, we're going to get this. Let's isolate lambda and see what happens. We get that lambda is equal to 2x plus y over 2x, and that lambda is equal to x plus 2y over 2y. Meaning, we can set those two equations equal to each other. Simplifying these two equations down, we get that y squared is equal to x squared. This right here is the thing that we're looking for, because we can plug this back in to the boundary equation. By doing that, we will be able to find our critical points that are on the boundary curve. First, we plug in x squared for y squared. Simplifying that down, we finally get that x can be equal to plus or minus root 2 over 2. Now let's substitute y squared in for x squared, and we get the same thing. We have 4 numbers here. Since we have 2 points for x and 2 points for y, it means we have 4 critical points. Our critical points are root 2 over 2, comma root 2 over 2, negative root 2 over 2, comma root 2 over 2, root 2 over 2, comma negative root 2 over 2, and finally, negative root 2 over 2, comma negative root 2 over 2. These are going to be the critical points on the boundary. Our last step in this equation would be to plug all of these things into the original equation to find out our global maximums and minimums, but that's just plug and chug, so I think I'm going to skip over that for now. And that's literally Lagrange multipliers. Obviously, there is a lot of practice involved, and this is a pretty simple example, but it illustrates very, very well the basics. It's good to know that this stuff is understandable. On to physics. Let us first go over the voltage, current, and charge in a capacitor over time. I am not going to go over the proof for this stuff, specifically because it involves integration using separation of variables, which is not something that I'm supposed to learn until differential equations next semester. What is going on at this school? But no matter, the equations themselves are pretty easy to understand. When you have a capacitor that is charging, you're going to have a different value for charge in that capacitor for every certain time. We can write this as a function. Charge Q of t, which is charge with respect to time. This is going to equal C times the electromotive force that the capacitor is connected to, times the quantity of 1 minus e to the negative t over RC power. Important little side note here, RC can be expressed in terms of tau, where tau is called the time constant. We can also know the voltage dropped across the capacitor, which is going to be equal to the electromotive force times the quantity of 1 minus e raised to the negative t divided by RC power. And finally, we can find the current that is going to be flowing through this capacitor. I, with respect to t, is going to be equal to the electromotive force divided by resistance times e to the negative t divided by RC power. When discharging, it's a different story. We can still write charge, voltage, and current in terms of t, but this time Q of t is going to equal Q naught, the initial charge inside the capacitor, times e to the negative t divided by RC power. Vc of t is going to equal Q naught divided by c times e to the negative t divided by RC power, and I of t is going to equal Q naught over RC times e raised to the negative t divided by RC power. The important thing to recognize is that when the capacitor is charging and when the capacitor is discharging, it is doing so at an exponential rate, meaning that the capacitor will only be fully charged or discharged after a very, very, very long time. It is because of this relationship that we can write the behaviors of capacitors when they begin charging and after they have been charging for a very, very long time. When time is much less than R times C, the capacitor is going to be equivalent to a short wire or short circuit. The current running through is going to be equal to the electromotive force divided by R. That's just Ohm's law. This is when the capacitor is initially uncharged. There is no charge in this capacitor. If the capacitor does start with a charge, then for the briefest of times it is going to act like a battery, where the electromotive force that it supplies is going to be equal to the charge initially inside divided by C. This is what happens when it starts uncharged, and this is what happens when it starts charged. Now let's look at the behavior of capacitors after a very long time. As it turns out, it doesn't matter if it starts charged or uncharged in this case. A capacitor, after a very, very long time, will begin to act like a broken wire or broken circuit. So to recap, if you start with a charged capacitor, for a very short time that capacitor will act like a battery. If you start with an uncharged capacitor, for a very short time that capacitor will act like a wire. But after a very long time, no matter what capacitor you start with, you are going to end up with a capacitor acting like a broken wire. Alright, I'm voting that that's going to be about it for tonight. We started very briefly on magnetism today, but there really wasn't that much to cover, so I think that's going to be a problem for a later date. I have my citizenship and public ethics midterm tomorrow. I feel very confident on it. I've been studying, so I'm hoping that's going to go well. Hoping? I know it's going to go well. Heck yeah. Confidence is key. We're so close to spring break. Fair warning, there's going to be around a week hiatus before I begin making videos again. I think, if I'm able to figure out how I'm gonna make videos from home. But that's a future me problem. I'm sure future me will be smarter and wiser, and he will know exactly how to take care of it. And I also know that future me will be very happy to see y'all when I do it. But in the meantime, thank you all so much for watching. See you tomorrow.